All right, so for today's lecture, you should have read sections 1.4 through 1.6 first. And as usual, watching the video is not a replacement for reading it. I'm not going to go over everything that's in here. I'm going to go over some stuff that I think is important and also just stuff that I think may require extra attention and just stuff that I think would be helpful. But you should read this first. So I'm actually going to start by just solving a problem, and actually, technically, for this problem, you probably don't really need to read this first. For the rest of the lecture, you will need to have read this first, but this first problem is kind of basic. I just thought I would start with solving a basic problem. This is out of the exercises at the end of chapter 1, and I'm going to give you some of these to do for homework. So I decided to do number 3, which says we have a graph G of order 26. So it has 26 vertices, size 58, so it has 58 edges. 5 of the vertices have degree 4, 6 of the vertices have degree 5, and 7 of the vertices have degree 6. All of the other vertices that I didn't mention have the same degree. And we're not telling you what that degree is. And the question is, what would that degree have to be? So yeah, you may want to just pause the video and think for a minute about how you would do that, because that could be more helpful than just watching me do it. So yeah, now's your chance to do that. But regardless of whether you paused or not, I'll now go ahead and do it. So basically, what we're going to do is we're going to consider the sum of all the degrees, and we're going to use the handshake lemma, or the it's also called the first theorem of graph theory in the book. And if you paused and you tried to solve it and you couldn't think of anything, maybe now that I told you that you're going to use those things, maybe you want to pause again and try again. Think about the degree sum and the handshake lemma. But let me go ahead and do it. So say the other... Okay, we had 26 total vertices. 5 of them are here, 6 of them are here, and 7 of them are here. So that's a total of 18. So there's a total of 26 vertices, and I know the degrees of 18 of them. I know these 5, these 6, and these 7. So that means there's another 8 vertices whose degrees I don't know, but I know they all have the same degree, whatever it is, say D. Then if I do the degree sum in G, meaning I add up all the degrees of all the vertices, well, that would be, I've got 5 vertices, and each of them has degree 4. So I would have 5 4s, and then I would have 6 5s, and then I would have 7 6s, and then I would also have 8 of whatever this is. And what do we know about the sum of all the degrees in a graph? By the handshaking lemma, that's twice the number of edges. And we were told that the number of edges is 58. And now we have an equation. We're just going to solve it. Yeah, I'm tempted to just skip the rest, but let me do this properly. So I've got 20 plus 30. I guess I'd actually make sure to write this down so I don't make a mistake. 42 plus 8D equals 116. And this is 50, so 92. Okay, so bear with me. I'm going to attempt to do two things at once here. So these add up to 92, and I'd like to subtract this over, and that's going to give me 24, isn't it? And this is good. It would be bad if I didn't get a whole number, right? That wouldn't make any sense. But I do get a whole number. If I didn't get a whole number, I'd know I must have made a mistake. So yeah, it must be that all the other vertices have degree 3. So yeah, it wasn't that hard. So now I'm going to do another one that's out of the exercise at the end of chapter 1. And for this, you really do have to have read the sections 1.4 through 1.6. In particular, I think it's 1.6 that has the graph operations. We're going to prove that there's no self-complementary graph of even order. But first, we're going to talk about what that means just a little bit. And actually, as we're talking about what that means, let me point out the note that there is a self-complementary graph of odd order. We're supposed to prove that there's no self-complementary graph of even order, but as I talk about what that means, let me just point out the fact that there is a self-complementary graph of odd order. In particular, let's talk about this graph. This is a graph that we've seen before. This is called a cycle. Oops, that's not how numbers go. The next number is 4, and then 5. So this is a cycle of length 5. And what does it mean to be self-complementary? Well, you have to talk about the complement. So here's a graph. It's the complement of a graph, which we write with a bar over it, right? Sorry, I'm just making sure we have the same notation here. Yes, okay, yeah, sorry. The notation I was making sure I'm using the same notation that's in the book. Right, so we're good. But the complement of a graph, it has the same vertices, so I'm just going to draw a 1, a 2, a 3, a 4, a 5. And it doesn't have any of the edges that G has, so it's not going to have any of these edges. And it has all the possible edges that G doesn't have. So if 2 and 5 are not adjacent, then 2 and 5 are going to be adjacent in the complement, right? And in fact, all of the pairs of vertices that aren't adjacent, so like 1 is now going to be adjacent to 3, 1 is also going to be adjacent to 4, 2 is going to be adjacent to 5, 2 is also going to be adjacent to 4, and 3 is going to be adjacent to 1, it's also going to be adjacent to 5. And that's it. That's all of the edges that G didn't have. And what I'm saying is that G is self-complementary since for this particular graph, it happens to be the case that G is isomorphic to its complement. We talked about these two graphs before, last lecture, and we showed that they're isomorphic. But yeah, actually, this was, well, the vertices had different names at the time, but the picture looked the same, and this will work the same. I'm just going to make an explicit isomorphism here, and I'll go fast. If you remember, the way this went was as I go around here, I go around here. So if I go 1, 2, 3, 4, 5, I can go 1, 3, 5, 2, 4. 1, 3, 5, 2, 4. That's an isomorphism. And so that's what makes G a self-complementary graph. And actually, so sorry, but I think I wrote down the problem wrong. Making mistakes today, but it'll be all right. Yeah. Okay. This was supposed to say regular. There's no regular self-complementary graph of even order. And the one that we just talked about, of course, it had odd order, but it was regular. All right, this was 2 regular. Every vertex has degree 2. So we showed that there is a regular self-complementary graph of odd order, and now we're going to show that there is not a regular self-complementary graph of even order. Now, what would we know about this? And so of course, now's another opportunity for you to pause the video and see if you can think of anything. But I'll make some comments first, and if you can't think of anything, then maybe you can listen to my comments and then pause the video again and see if you can think of anything. But why did this picture work? Like, why were we able to come up with a regular self-complementary graph? In order for that to work, if G is regular and G is going to be isomorphic to its complement, then its complement needs to also be regular. And in fact, we know that isomorphic graphs, they have the same degree sequence. So if all the degrees here are the same number, say R, like this is an R regular graph, all the degrees here would be R, and that would mean that all the degrees here would also need to be R. And we were able to make that work because this is a 2 regular graph, and this is also a 2 regular graph. But right, let's talk about how this could work if it had even order. So let's basically shoot for a proof by contradiction. So we'll suppose that we do have a regular self-complementary graph of even order. So suppose it's self-complementary. G has even order and is R regular. Then let's talk about how G complement would have to be R regular. So G complement would also be R regular because they are isomorphic. But then what? If I look at, say, the vertex 1, 1 has certain neighbors in this graph. The neighbors are just the vertices that it's adjacent to. So it's adjacent to 2 and 5 in this graph. And then 1 has different neighbors in this graph. It has the neighbors 3 and 4. But between this graph and this graph, if I look at all the neighbors of 1 in this graph and then all the neighbors of 1 in this graph, it's everything. It's 2, 3, 4, and 5. Like 1 has neighbors 2 and 5 here, and it has neighbors 3 and 4 here. But if I combine the two, so to speak, 1 has every possible neighbor. And actually, that's true of every other vertex as well. Like, let's look at the neighbors of, say, the vertex 4. Over here, it's 3 and 5. Over here, it's 1 and 2. And so that's everything. So basically, here's what I'm saying. If I add the degree of a vertex in G to the degree of the same vertex in G complement, between G and G complement, it's adjacent to every other vertex. And say there's, let me insert something here. Let's say the order is n. In other words, say in this graph of order 5, if I say I'm looking at 1 and I'm looking at all the neighbors of 1, there's 4 neighbors of 1. There's 2 of them here and 2 of them here. And that's because 1 is adjacent to every vertex except for itself. And that's how this is going to be in general. And again, it's just because the complement has every edge that G doesn't have. So between the original graph and the complement, each vertex is going to be adjacent to everything but itself. So if I add the degree in G plus the degree in G complement, I'm going to get n minus 1. It's adjacent to all of the vertices except itself. So what do we have? Well, the degree of V in G is R. The degree in G complement is also R, because they're both R regular. So that equals n minus 1. So 2R equals n minus 1. N's an even number, so this would be an odd number, and that's a contradiction. So when I reach a contradiction, I draw arrows pointing to each other, and this is not just me. This is a common symbol for a contradiction. So that's the end of the proof, because this was a proof by contradiction. So this is a proof box that I put at the end of a proof. Okay, so actually I'll probably cut that video off now and start another one.